prioritize muscles, like superficial to deep is like the order of priority. So it's not like all those tiny little guys around the side. I remember they're probably not going to come up. I mean, maybe. I don't know. Memorize 400 some muscles in 2 weeks.
Like 600 something.
No, I know.
Okay.
We have to be studying joints too. Yeah, it's like everything going on all at once.
So let's pick up where we left off, shall we? So we talked a little bit about this one. I remember doing a little bit of performance art for that one. The swim move, the baseball pitch, right? The curved ball, basically, that's that one. And so when you're taking a look at flexion and extension, remember flexion, you're making the angle about your joint more acute. Extension, you're making it more obtuse. So obviously, if you're looking at a hinge joint, for instance, like your elbow, then basically you've got flexion. So the flexors, the extensors, same thing with your hand, right? Your extensors are going to be on the top of your forearm, right? That's kind of what we're studying right now, some of those muscles. And not only that, but remember your extensors in your hand, because we've got like a really manipulable hand, there's a lot of extensors in there, right? So like on this side, for instance, you'll see extensors of your carpals, right, which is your wrist. So a lot of carpal extensors. You have some ulnar carpal extensors, right? So basically extensor carpi ulnaris, which is on this side. And then you have extensor digitorum, right, which is basically extension of the digits. Remember, you have extensor digitorum longus, which is in your leg, right? So that's the big one. That's the one that's right next to tibialis anterior. And then you start to rotate over to the radial side where your extensors start to take on the radial names, right? So like, for instance, extensor carpi radialis, right? And that's the nice thing about these extensors and flexors of the forearm is the names are actually indicative of their attachments and their functions, right? So a lot of times it saves you sometimes if you're clever about it and you know what you're looking at, right? So you could be looking at some little itty bitty muscle next to similarly shaped itty bitty muscles. And the idea is like, well, they all look the same to me. So which one's this? Well, if you just sort of slow down, keep breathing, and just sort of rationalize it out, a lot of times you can get pretty close to where it is. It's like, well, wait a minute. Let's just think about this for a second. Where am I in the body? Well, it looks like I'm on the extensor side of the forearm. But where in terms of lateral medial relation? Well, it looks like I'm on the radial side. So this has clearly got to be some sort of an extensor on the radial side. And it appears as though the tendon is attaching to the carpals. So this is a pretty good deduction. And you got a better than at least you're not just blindly guessing. So you can kind of almost reason it out and figure it out. It's like, well, I think this might, I'm not sure, but I think this might be extensor carpi radialis, right? Just because of its position. It's the nice thing about these muscles. There's a lot of them and they're all the same shape, but the names of will tip you off. Now, in terms of flexion, right? As you start to rotate, this is the thing I love about the arm, is you can start one place and you can just start rotating around, right? So pretty soon, right after extensor extensor carpi radialis, you're going to run into brachioradialis, right? So brachium, that's the brachium, right? Brachioradialis on the radial side. So that's basically this big muscle right there that kind of goes like that. So that's giving you an attachment phrasing, right? So one end of it is attached to the brachium, the other end is attached to the radius, okay? And then that's kind of like your boundary. And then after that, you start to switch over to the flexors because now you're on the flexion side of things, right? And it's the same convention, right? So oftentimes you'll get, say, for instance, flexor carpi radialis longus and brevis. You have two of them, right? And then you'll get a big teardrop shaped one in the middle, which is palmaris longus. And you can actually see the tendon fans out in the middle of the hand. So the palmaris, it's basically the one that flexes the palm, okay? So that's your palmaris longus. It's kind of like the flexor counterpart to your extensor digitorum, okay? And then as you continue to rotate around, then your flexors start to take on the ulnar terminology, right? Then you start to get into flexor carpi ulnaris. And then in the middle of all that mess, we're missing one, right? There's a flexor, actually it's on this side, an extensor digiti minimi. So you little minimal digit extensor, right? So you kind of have flexors, extensors, carpal, ulnar, radial, and then the flexors, right? So radial and ulnar. Having that basic breakdown of orientation a lot of times can at least get you somewhere close to guessing on an exam. And that's the reason why you want to kind of use that orientation. So if you haven't had a chance to really just take it in, the best place to do this is we try to use it with the cats. But what I'm seeing in the forearms of the cat so far is close, but not quite where I want it to be. So there's a couple of things in there that seem to be pretty clear. William has a really nice leg. The quad group is really nice in their cat. So take a look at that one. The lower leg is actually pretty good as well. I think last time we went through tibialis anterior, I think we located the peroneus group, right? We talked about that a little bit. We were clearly able to see extensor digitorum longus and then soleus and then gastrocnemius. So there's a lot of upper and lower leg definition in the cat that William and his crew have been working on. I think in terms of upper arm, I'm looking for a good bicep, tricep, brachial definition. So I'm still looking for that one. Pardon me?
We'll get that today.
Yeah, and so what I want to do by the end of the day is I want to designate who's our exam cat. I'm looking right now that maybe we might have one.
Ours is good for back stuff.
Yeah, so it'll depend. I might have two, but I definitely have a solid one. So what I've seen so far from what William and crew have been digging up, I think has been some of it is very good. The forearms not quite there in any of the cats that I've seen, but there are some other things that I've seen there. So like I said, they're close. They're really, really close. And that'll probably be a game day decision, to be quite honest with you. So prepare to expect it. That may be one of those ones where I show up early to set these things up in the morning. And I'm just going to take a look at the cats and be like, I can't do it. And that'll be a late scratch. Okay. And that's the thing I'll tell you about in the hallway. It's like, by the way, planning on two, there's only one. Or I was planning on one. Guess what? There's two. So that's that. So here's your other hinge joint, right? So your knee, so the flexion is basically lifting your knee up versus extension, which is putting it back down. And so this is also movement. Dorsiflexion, plantar flexion, that's basically, right, pointing your toes down, that's plantar flexion. Notice you're flexing toward the region. Your plantar area is the sole of your foot. So you're flexing toward your plantar. Dorsiflexion, you're pointing toward the dorsal area of your foot, which is the top of your foot. Right, so that's what I call dorsiflexion. Adduction, abduction, right? So this is rotation about your shoulder, of course. To abduct means to go away from the body. To adduct means to go toward it. A lot of you guys have run into the upper leg thigh muscles, right? The adductor magnus, you guys have run into adductor longus. Those are adductors. So what are they doing? They're moving the leg in toward the midline. So those are the ones that you're doing when you're kind of like squeezing and doing those thigh master things, right? Where you're squeezing inward. Notice they're not enormous, right? Because you don't have a lot of bulk load associated with that direction, right? So that's the reason why they're not as well developed. And of course, abduction means you're going the opposite direction itself. In terms of your hand, your center point is not your midline. Your center point of reference is the middle of your palm, right? So to abduct means to run away from the center of your palm. So that's abduction. Adduction would be to bring them together, right? And then of course our rotation. So this is kind of a nice one. This is just basically a swivel about the shoulder. So this is a movement largely of the shoulder girdle. Notice your elbow's not moving. It's a hinge joint, right? Now it's basically moving in this direction. So in this case, what you're doing is you're pivoting your shoulder ever so slightly. You're going to do a medial rotation or lateral rotation. Okay. And then, of course, circumduction we talked about, which is just basically drawing a line without the twist in the air. Then, of course, we already talked about pronation, right? So pronation basically means to rotate toward the prone position, and the supination is to rotate toward the supine position. And of course, we talked a little bit about that complex move, right? The swim move, where you have a combination of circumduction plus pronation. So you're kind of going like this, you're rolling over like that. But notice you also have a little bit of that medial rotation going on there. So there's actually, if you think about it, if you want to separate all three of them apart, you have three different movements going on there, right? You have a circumduction with a pronation with a medial rotation, right? Like that, as you come across your body. Some lesser known ones, right? Elevation, depression, that's basically your mandible. So to elevate, close your mouth, depress, open it, right? Some of your muscles are actually named after this, right? Like depressor angularis, things like that, right? That's a depression. That's a muscle that's involved in that depression thing. When you get to the face muscles, if you haven't already, you'll see some of those in there. You'll hear them referred to elevators and depressors. Protraction, retraction, that's sticking your jaw out, right? So basically protraction is sliding your jaw out like that. Retraction is pulling it back in. Excursion is like really rare. Don't really cover that one. Actually, most books don't even cover excursion. That's how uncommon it is. Reposition, opposition, the opposable thumb, right? Just think of the opposable thumb. What this is not abduction, adduction, but it's basically taking your thumb and touching your fingers with it. That's opposition. Reposition is undoing. Okay. And then an inversion, eversion is basically what you're doing with your feet. So if you're like me, from time to time, to change the stress angles, you'll stand on the edges of your feet. So that one is inversion. It's the direction that your soles are pointing. So we have a little bit of play for inversion, right? Eversion is basically if I turn them the other way and turn the soles outward. Okay, we don't have as much for that, right? And then we have combination movement. So here's your protraction, retraction. So you can see you're sticking your jaw out versus sucking it back in. Then elevation, depression. The mandible is a common one. Also shrugging your shoulders. That's an elevation depression as well. Right. And then excursion. You're grinding your teeth. Right. So that's cows do that. So I got a little cow movement going on there, right? By the way, excursion is actually just sliding back and forth, medial lateral. Cows, technically speaking, don't do this. Cows actually have a more rotational sort of thing. They're actually moving in a circle. So their jaw actually goes up and over, grinds, and then goes back down and up and over, goes in. So they're done kind of like. Exactly. And it comes back up and they just add it to their little pile. So that's what chewing your cud is called, right? You usually think of it as a term that was associated with somebody thinking about something and they won't let it go. They just kind of keep chipping away at it. Well, that's basically what a cow does. They're basically kind of eating their little grass bolus and they're just kind of eating it pretty much progressively all day long. So it's great to be a cow, right? Unless, of course, they turn you into a hamburger, then it's not so great. But it's great to be a cow in India, right? Right, because they're sacred there. Or at least last time I checked, they were. That may be changing actually with the 21st century. So, for the most part, this is opposition reposition. Right? Think opposable thumb. Right, that's one of our big innovations. Is that opposable thumb? And of course, reposition is basically turning it back. And of course, inversion, eversion, it doesn't really show here very well, right? But that's basically turning your soles inward versus outward, essentially. Well, there you have it. In silence while we listen to Benson yell at his students almost constantly. You should have heard it last semester in the same class. My students were just like, "What is he talking about?" I mean, that's like he was so loud. We were just like,
It's just so passionate about it.
you could call it that. Yeah, that's one way to look at it. No, I was picking on him about it. He's got an accelerated class, so they're like meeting for like 6 hours a day. It's like crazy. So he's got to be like over the top to keep these folks like involved, to keep them from dying on him. We are moving on to another chapter. It's true. So now it's going to be muscle physiology and histology.
Have you seen that? Like when they do this, it's like you know how we have basic and like yes, it's so funny. It can barely breathe.
Okay. So muscle physiology. I'm going to try to get through as much of this before the exam. So the idea is to have a good chunk of this on there. A lot of these in the neurophysiology, there will be a lot of overlap there. So the neurophysiology, even though it looks big, will actually benefit from this particular chapter here because they do kind of dovetail a little bit. So let's take a look at the muscular system. So the muscular system, obviously we've learned a little bit about this from histology, right, from the histology section. And so I don't want to belabor what we've already covered, right? Because we got a lot of stuff we haven't covered and we want to really focus in on the new material. So some of the things we already know, right? What do we already know? We already know that your muscle tissue is broken up into three different types of muscle, right? So you got skeletal, which is the mobile stuff, right? This is the stuff of body movements. That's what we're looking at. Smooth muscle, which is involuntary stuff. When we associate this with organ muscles, right? So how your organs move and your autonomic stuff moves. That is to basically say your involuntary things move. Your eye muscles are smooth. Most anything that is not skeletal is smooth. I think the cardiac is only found in the heart, and it's nowhere else. So pretty much a good chunk of your muscle tissue is skeletal because we do have a lot of ambulation. We've got a lot of stuff to move around in our body. And then when it comes to organs and non-moving stuff, functional stuff, I like to think of physiological stuff, right? That usually encompasses smooth muscle. And so you can imagine that the majority of what you see when you get into AMP2 is smooth muscle, because that's the muscle of all of your viscera. Okay. So let's just take a quick breakdown of the muscle types. So first of all, you can see you got your skeletal muscle, which tends to be long and cylindrical in nature, multinucleate typically. and they're heavily striated. So here you can see the striations associated with the skeletal muscle. Smooth muscle tends to have single nuclei per cell, and they tend to basically have this sort of gummy worm look to them. And so this is a really good image of smooth muscle. You can see it looks like a little clustering of gummy worms, basically, that are kind of sliding across next to each other. And then, of course, cardiac muscle is basically muscle that is interconnected. So you can see actually how they have these little interconnecting branches to each other. In addition to this, you can actually also see that they've got these intercalated discs. This is where those gap junctions are. You can kind of see them a little bit, but this is where those gap junctions are. It forms the boundary of one cell to another. Also striated. So this is just kind of more data on them. Most of this I covered, right? I already talked a little bit about cell shape. The nuclei, cardiac muscles are also single nucleus. And a little bit about their connections. For instance, intercalated discs, which are basically gap junctions in between them. So basically, you kind of have your basic rundown, right? So this is stuff that we already learned about a little bit in the histology chapter. We just kind of got it all together. And this is the reason why I put all this stuff in the table, right? Because the idea here is that this is just the vital stats of your basic muscle tissues, right? Most of our chapter in physiology and most of our studies in lab are associated with skeletal muscle. That's what we're working on, okay? So what about what they do? So basically, body movement controls what skeletal muscles do. They're voluntary. However, they're also involuntary, although that's a very small grouping of them, because you do have reflexes, right? Smooth muscles are almost all involuntary. So you're not controlling these or thinking about these. So this basically has a whole bunch of activities, all of them associated with the activities of an organ. Cardiac muscle, also involuntary, and largely this is what it does. It pumps blood for a living. That's its job, okay? So when you get the cardiovascular system in AMP2, then you kind of just double down on the function of these with the understanding that largely for the most part, we've already kind of looked at its structure. We kind of diagnosed it a little bit in histology. And then we kind of have our vital stats kind of all in one place. So it's just basic structural stuff. And we'll talk a little bit more about that structure, especially in the skeletal muscle as we go on, because the structure actually does lead us to our function. So what exactly does the muscular system do? Well, just like with the skeletal system, right? There's sort of the big ones that we always think of. First of all, movement, right? That's probably the number one that somebody would come up with. Sort of like Family Feud. That would be the survey's number one choice right there, right? Probably muscle movement. A lot of people would probably think posture, right? Those postural muscles. Those are ones that are oftentimes relatively involuntary or lightly voluntary. Some who actually are a little more clever might come up with respiration, right? And most people are thinking of what? Which muscle? The diaphragm, right? However, there's more than just the diaphragm involved in respiration. Intercostals are in there, scalenes are in there. So there's a few muscles that are associated with that one. Pectoralis minor is in there, right? So there's a few of them in there, not just the diaphragm. Then we start to get to the physiological role. Right? So how about muscles as your heat generator? Right? This is your hot water bottle. This is what produces and maintains body heat. So if you think about it, this is also the reason why when your core body temperature starts to drop, called hypothermia, you start to shiver. Do you have any control over that shivering? I mean, you can sort of try. You can try. You can fight it, but it's not successful, is it? Yeah. Right. So that why is the body doing that? Because it's trying to raise your core body temperature because your muscles are your heat generator. Okay, that's how you get your body heat. Communication, probably didn't think about that one, huh? So that's another one that kind of goes unnoticed. Of course, your organs, constriction of your organs and your blood vessels, that's a smooth muscle function. Of course, contraction of the heart. Right? So I would argue that 4, 5, 6, and 7 are like the highest priority. Because these basically form life and death. The other stuff, well, respiratory. Okay, we'll toss respiratory there too. Because I mean, it's kind of, I mean, it sucks not to breathe, right? I mean, it's kind of a little hard to stay alive and not breathe at the same time. Okay, so we'll toss 3 in there, right? But when it comes to 1 and 2, which is mostly what people are limited to thinking about, you know how I know this? Because we got entire degree pathways that only focus on 1 and 2. They're called chiropractors. They're called chiropractors. He didn't. He's louder than me, even when I'm not like struggling with vocal cords. I'm pretty loud, but he's obnoxious. Good guy, but obnoxious in a lovable sort of way, right? So none of that, but kinesiology, there's another one, right? Physical therapy, right? I mean, most of where you're living is 1 and 2. I would argue those are the least important on this list. You know, I know that because you can live and not be able to move a muscle, except your heart. Heart notwithstanding. You may not want to live, but you can, right? You can live and have non-functional postural muscles. We know this, right? Because what I described is something relatively close to quadriplegia. And quadriplegics can live. They just can't move. You know why? Because they've lost the capacity to do 1 and 2, but they can still do 3 through 7. Because theirs was a damage that happened to skeletal muscles, not to smooth and cardiac. Right. So that kind of puts it in perspective, which is one of the reasons why I'm not a chiropractor, right? Because there's bigger fish to fry, much, much bigger fish to fry. Okay, so let's take a look at what some of these properties are. This is true for all muscle tissues, but here again, I'm going to basically kind of preface this with a caveat. Remember, at this particular point, what we've got is a focus on skeletal. That's where we are. Because that's where that's where we live, right? I mean, yes, is it nice to have your heart contracting? Of course, right? Because otherwise you'd be dead. Is it nice to have all your smooth muscles working normally? Yes, of course, right? Because otherwise you'd be dead. But let's face it, what we really are interested in and fascinated by is how we move. And it's our ambulation, right? So that's the reason why we tend to be skeletal muscle specific, because it forms just about everything that's intuitive to our system. So what's some of the general basic things about muscle tissue? So first of all muscle tissue has a property about them that we refer to as contractility. And what does that mean? So it basically means how well can you shorten? That's what it is. So for a muscle to contract means the muscle shortens. So if you have good contractility, that means you have a good, strong ability to shorten with force, right? Because the idea is you're responding to a load, you're adding force to something. And so your ability to contract is an important thing. Now we tend to talk less about contractility in skeletal muscles, but it's a big deal in cardiac, Actually, it's one of the cardiodynamic metrics that we really talk about when we take a look at cardiovascular system health. Contractility is incredibly important. It also has to be an excitable tissue. What does that mean? That means you have to respond to a stimulus. That is nervous stimulus. You have to be able to receive instructions. So it's not good enough for you to be able to shorten. You have to know when to shorten and how to respond. That's your excitability. You're able to basically receive instruction. Another property you have to have is extensibility. So essentially you have to be able to stretch beyond your normal resting length. But guess what? Not stretch and never come back. You have to be able to stretch and recontract. That's extensibility. Not just stretch and snap, right? Think of it as sort of like spandex, perfect, right? That's got a good extensibility. It is able to stretch out, but when that force is removed, it's able to recontract back or recoil. So that's good extensibility. And of course, in order to do that, that's related to elasticity, which is your recoil. So it's not just about stretch and contract, but it's about stretch and unstretch. So that's what recoil is. This is the unstretch. Notice I said unstretch as a foil because in the previous one, we're talking about contraction, right? So unstretching is not the same as contraction. It's undoing your stretch. So this is where the spandex model sort of breaks down a little bit, because the spandex model actually doesn't have extensibility. It has elasticity, right? Which is your ability to stretch out. And then when you remove the force, it recoils back to its original shape. Where extensibility adds to that is it's able to contract even further beyond its original shape. So that's where the muscle is. So it has to be able to stretch, recoil, that's elasticity, and then contract to get smaller than its original shape. So all muscle tissue has to be able to have those four properties in varying degrees. So let's take a look at the actual anatomy of muscle itself. So obviously there's a lot of connective tissue in there. And this is a system, a layering system that we're going to see that you really, 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 really want to get comfortable with. Because this same type of layering system is a similar one that we see in neurons and in nerves. Right, so let's take a look at it. We're talking about connective tissue coverings. So ultimately, the first layer that you see is what's called the epimysium. This is like a connective tissue sheet. That basically surrounds an entire muscle that's composed of what's called many fascicles. So basically, we'll talk about fascicles here in just a second. Well, the reason why we'll talk about that is because it's associated with the next liner, the paramysium. So the epimysium is important because it's sort of like the outerish layer. What this will basically do is this will basically interface with the fascia. So the fascia basically is like a membrane of connective tissue. That's what the fascia is. So when you guys have been cutting into the cats and you see that kind of like membranous sheet that's wrapped around it, that's fascia. When you kind of pull it up a little bit, you see the cobwebby look in between muscles, that's fascia. That's a layer of fascia that's in between those muscles. So there's multiple layers of fascia, connective tissue layers that bundles everything together. This one is the outermost one. And so this basically will merge with the outer layer of that outer membrane. It'll also basically bind together adjacent muscles and muscles to skin, right? So what a lot of you guys were doing was, if you're pulling up the skin, you were noticing a lot of this connective tissue stuff that's stuck to the muscles. That's part of that epimysium stuff, right? That's that connective tissue that's basically fastening these muscles to the overlying skin, and then muscles to muscles themselves, bundling them together. Okay, let's take a look at the next layer, which is the perimysium. So peri means around the muscle. So this is basically another connective tissue layer, but in this case, it's basically surrounding a group of muscle fibers. Now, a little bit of muscleology, right? Muscle speak. When you hear the term fiber, muscle fiber, this basically is synonymous with a cell. So a muscle fiber is a muscle cell. Now, what happens is you basically have groups of muscle fibers that are bundled together in what's referred to as fascicles. So if you take a look at a fascicle, it's this large bundling of muscle fibers. And the perimysium is surrounding this fascicle. Now, the good thing about this is, in this area, you can have blood vessels interweaving through these fascicles. You could have nerves, things like that. So this is a good place to sort of interject a lot of this communication to the muscle itself. The last layer and the bottom layer, the inner layers, and the endomysium. This means inside muscle. So this is a connective tissue layer that's actually separating the individual muscle fibers within a fascicle. So if I were to take a look at this thing here and blow it up, what I would see is my endomysium wrapped around each one of my little muscle fibers. Then my perimysium would be wrapped around the fascicle. And then multiple fascicles together would be wrapped by the epimysium. So when you're looking at basically interconnecting tendons and things like that, these membranous sheets of connective tissue, this is all basically being attached with this kind of connective tissue outer layer, typically. Usually it's an outgrowth or an extension of the epimysium. That's where a lot of this kind of connective tissue is coming from, the collagen especially, that's associated with tendons. So let's just basically talk nerves and blood vessels first, and then we'll take a look at the unit system. So basically what drives skeletal muscle is motor neurons, right? So these are the ones that basically will actually stimulate and carry the message to your skeletal muscles. So when you take a look at a single motor neuron, generally speaking, you will actually be interfacing with multiple muscle fibers. Remember, a muscle fiber is a muscle cell. So for one motor neuron, you're actually communicating to multiple muscle cells. And so there's not a muscle fiber that doesn't have some sort of a neural connection. So that is to say that each muscle fiber is supplied by a piece of a motor neuron somewhere. generally speaking, in addition to arteries and veins that you have permeating through this connective tissue layer, you also have capillary beds that are in and around the muscles, feeding the muscle cells, because remember, these guys are actively contracting, they're actively moving all the time, so they're energy consumers. So you have a lot of blood supply to those muscles. So they have to consume nutrients in order to be able to contract. So what it looks like. So here's your muscle. So your muscular fascia is this kind of overlying connective tissue membrane. And then the outer layer that surrounds these bundles of fascicles, so you can see it all the way through here. So this layer right here, that is the epimysium. You've got blood vessels here, you got a neuron there as well. Then in and around the actual fascicles is going to be your perimysium. Notice the peri and the epi kind of bleed together a little bit sometimes. And then as you go deeper into, so this is a fiber, a nerve, that's fiber, not fascicle, that's fiber. F for fiber. Just ignore that right there. Right, so that's a muscle fiber. And so you can see that you have surrounding the muscle fibers this sort of light purplish color. That's the endomysium, which is surrounding the fibers. So the endomysium surrounds the fibers. The perimysium surrounds the fascicles, which is a bundle of fibers. The epimysium surrounds the bundle of fascicles. So your muscle is a lot like a suspension bridge cable. Right, so if you've ever seen a suspension bridge cable cut in cross section, like the Golden Gate Bridge, or the Bay Bridge, or the Brooklyn Bridge.
It's just a concept of multiple cables all wrapped around each other, from small all the way to large.
Yeah, it's like nested cables. It's like a cable of cables, right? So the big cable is actually made of smaller cables, which themselves are made of smaller cables, which are made of smaller cables. And that's kind of what your muscles are like. Actually, muscle itself is like a big gamish, if you will, of these cable-like fascicles, which are a bundle of muscle fibers. And I like this image because it can show you clearly the way the vasculature and the neural connections are basically interlacing all of these fascicles, weaving throughout the entire muscle tissue. And so these are good micrographs, so you can actually see some of these liners. So you can see you're looking down the end of it, so you can see these actual liners there. That's that epimysium, endomysium in this particular case. Perimysium, that's those liners associated with those fibers. Okay. From now on, we're focusing on skeletal muscle. So when you take a look at skeletal muscle, the biggest question that we first run into is where do they come from, right? How do we get them? Well, when you're in embryonic development, one of the things that you'll notice is that you have a group of cells. Remember, blast cells are developmental cells. These are cells that are just laying down new embryonic tissue. And a myoblast is a muscle cell that's laying down new embryonic tissue, right? So this is basically muscle. This is laying down embryonic tissue. So a myoblast basically is a preliminary or a prototype of a muscle cell. So it's like not really a muscle cell just yet. It's like the beginning of one. So how do skeletal muscles become multinuclear? right? That's the big question here. There's really only one or two ways. Number one is you can go through mitosis, duplicate and separate your nucleus, but don't go through kinesis. So if you don't do it through cytokinesis, what you have is a cell with two nuclei in it. If you do that again, then you'll have a cell with four nuclei in it, and so forth. Okay, so that's one way to do it. The other way to do it is to do what skeletal muscles do. So what they do is they fuse their myoblasts. So they take basically one little myoblastic cell with the nucleus in it, and it fuses with another little myoblastic cell with a nucleus in it. So when these two cells fuse, they create this big, long cell with two nuclei in it. And so this basically over time will give you this sort of large multinucleated cell. Generally speaking, the average skeletal muscle can be up to millimeters in length. Think about this for a second. How big is that? That's visible with the naked eye. 1 millimeter is a tenth of a centimeter. It's small, but you can actually read off a millimeter on the ruler. That is big from a microscopic, but it gets even bigger, right? So you can get up to like a foot. So we're talking some like really, really long muscle cells. And then of course your diameters are pretty tiny, right? So if they weren't so tiny in diameter, you probably could see them with the naked eye. But because they're so tiny in diameter, you can't really see them. So just to give you an idea, 100 microns, which is 100 micrometers, is about the threshold for your visible range. Below 100 micrometers, you're talking about you need a microscope to be able to see detail. So on its big side, it can get almost right up to visible with the naked eye in terms of a muscle cell itself. The hallmark, however, of skeletal muscle is its striations, right? So it's basically got these wonderful, charming little stripes. And that's what really allows it to sort of stand out. That's how you guys are able to sort of recognize it, like on the first exam. It's like, oh yeah, that's striated, so that's got to be skeletal muscle. That's really huge and striped. So they can extend. You can enlarge them, but typically you don't add to them. So like when you're taking a look at building bulk, you don't necessarily add new muscle cells. What you do is you add new material within a pre-existing muscle cell is usually how you add in bulk. So unless there's like damage. I mean, if you do damage, then obviously you have to replace the cell. That's a different situation, which oftentimes if you're building for bulks, a lot of times you do. So there's a little bit of both, but generally speaking, you usually increase your muscle cell capacity by increasing the contents inside the muscle cell itself. So let's take a look at a little bit of histology. So this is muscleology. So muscleology, what does this mean? It's basically the nomenclature of the muscles. By the way, there's nothing new here. This is all basically cell biology. The only difference is a lot of times muscles have their own name. It's the same structures that you learned about, like when you went through cell biology in general bio, when you learned the parts of the cell and things like that. It's the exact same thing. So for instance, here's a good example. The sarcolemma, right, which is a fancy term, simply is the plasma membrane of the muscle fiber. That's all it is. Nothing special there, just an average run-of-the-mill plasma membrane. We already talked about muscle fiber, right? So basically the muscle fiber is equal to the muscle cell. It's the same thing. Why muscle heads call it the fiber, I don't know. It's the cell. It's the muscle cell. Actually, I know why they call it the fiber, and it's actually not a muscle head thing, but it could have been changed to make it a little more uniform, but I'm not going to whoop on them too badly because at least it makes sense. The other one is sarcoplasm. That sounds official, doesn't it? Would impress your friends, laying sarcoplasm on them. Actually, you'll probably lose your friends if you lay sarcoplasm on them, so don't do that. What is this? It's basically the cytoplasm. That's all it is. It's the cytoplasm of a muscle fiber. Sarcoplasmic reticulum. What is that? It's the smooth endoplasmic reticulum of the muscle fiber. Right? That's all it is. There's nothing mysterious. It just sounds fancier by putting sarcoplasmic on there. Right? In this case, if you recall from general biology, those of you who had general biology, you know, one of the functions of the smooth endoplasmic reticulum is to store calcium. This is its function. This is what we're talking about in general bio when we say that one of the functions of smooth endoplasmic reticulum is to store calcium. You like that run on? I just like, right? So that's what it is. Now, here's a couple of things we want to, there's a special structure that we want to take a look at that's called the triad. And it's a really important structure in the muscle fiber itself. It's composed of what's called the T-tubules and the sarcoplasmic reticulum. Now, when you take a look at the T-tubules, what the T-tubules are is literally like an invagination of the cell membrane. What does that mean? Well, if you take the cell membrane, basically you have the cell membrane kind of on the surface. To invaginate means to basically kind of push it inward, right? That's basically what invagination is. So basically an invagination is kind of like a deep, almost like a mine shaft kind of a situation, right? Now that's what a T-tubule is. Now, on either side of the T-tubule are pieces of sarcoplasmic reticulum that form what's called the terminal cisterna. So the sarcoplasmic reticulum on either side will come up right next to the T-tubule, and then it'll form this kind of structure. This kind of swelling area. Which are called the terminal cisterna, these guys here. So together, these three form what's called the triad. So you have the T-tubule here in the middle, flanked by the two terminal cisternae. So these guys here are your triad. That's an important organization in order to achieve the function that the muscle fiber needs to achieve. And it's all driven by membrane dynamics and smooth endoplasmic reticulum dynamics. We'll talk about the purpose of the triad. It's part of the muscle contraction mechanism. So here's what it looked like. So here's your T-tubule, so you can see a deep invagination. But notice what happens here is it doesn't just go down linearly. It's actually like a pair of handcuffs. It actually surrounds these myofibrils that are actually inside the muscle fiber itself. And then you can see it's flanked by these terminal cisternae. So here's one terminal cisterna. Here's another terminal cisterna. So this is your triad right here. That whole area right there is a triad. And so you can see the triad actually permeates throughout the entire cell. So here's more triad going on over here, permeates all the way around the cell. So they're not showing the continuance here, but it basically wraps around these myofibrils. Okay, wait a minute. So I just mentioned something I didn't explain yet. What in the world is a myofibril? I just sort of threw it out there, right? So we know myo means muscle, fibril means something fibrous, so it's something has to do with fibrous muscle. So a myofibril, which is this big guy right here, is a complex of actin and myosin. That forms a contractile unit of the muscle itself. So the myofibrils are actually the ones that are doing the contracting. Hence the reason why your triad wraps itself around the myofibrils. It's kind of like a net. So if you notice, this is actually what it looks like right in here. This is actually what it looks like. So you see this continuous net that just basically rolls over each of the myofibrils and then interjects itself in between the myofibrils. So the myofibril is surrounded on all three sides, all three dimensions. It's surrounded by this triad system and by the sarcoplasmic reticulum. So it's kind of like spreading out this sort of sheet of gauze, wrapping it around these cylindrical myofibrils. So let's talk about those myofibrils. So obviously I've said that they're basically bundles of proteins. So they're big cables of proteins with these protein filaments in them. And these are the protein filaments that are responsible for contraction. So what's in them? So we have actin, number one. We have myosin, number two. Okay, wait a minute. Wait. So actin, we know, right? Actin is part of the cytoskeleton of the cell. So it's part of the natural framework of a cell. So it's always there. In the case of a muscle fiber, it's organized into these long filaments in these myofibrils. And actin, if you recall from general biology, is the smallest of the three cytoskeletal fibers, right? So you have actin, which is the smallest one, which is called a microfilament. Intermediate filaments, which were larger than actin, and you had microtubules, which were larger than that. So actin filaments are small. And typically they form small filamentous chains. That's the reason why they call it the thin filament. Myosin, on the other hand, is actually a type of motor protein. With a walking domain and a cargo domain. And it tends to form multiple associations with itself. So it tends to form what's called a thick filament. Now, between actin and myosin, you arrange these guys into a structure called a sarcomere. And this, the sarcomere, is the contractile unit of muscle tissue. So if you take a look at the myosin actin arrangement, so here's your actin. And then your myosin heads will attach to your actin. And basically these heads will basically slide things around. So we'll talk a little bit more about that. I don't want to get too much into this. I can already see as I'm writing it, I'm going to have to explain more than I want to right now. But what I want to do, the structure piece of it, we'll talk about and we'll look at later. So we'll look at the actual structure of myosin and actin together. We'll look at the sarcomeric unit, the components of the sarcomere, and we'll also look at the mechanism of shortening of the sarcomere and how the muscle actually shortens and contracts, right? So we'll talk about that. So here's your overall structure where we are now. So notice you have your muscle proper with your epimysium surrounding that big complex of fascicles. Then as you pull out individual fascicles, you can see that's where you're going to have your paramysium surrounding each of the fascicles. And then if you pull out a muscle fiber, so this is a muscle fiber, you can see, first of all, you have your endomysium here. But you can also see end on, you can see how the T tubules actually form this like ring-like structure, kind of like the rings on a six-pack, right? Oh, the old days, right? I mean, they don't. Do they still make six-packs with the rings on it? I'd say I never buy them. That's why, because it's like I just buy like the case. So I like go real, go home, right? So I don't have like the little ring thing anymore. Because the idea of like little animals getting stuck in there and dying was just such like, you know, I'd rather just not buy it really. Is it hard now? Oh, okay. So you gotta hang on to it. Oh, cool. Well, that's it. I mean, if you're gonna do it, you might as well have it be reusable. Right. Or just not do it at all. I mean,
Just kind of, circles.
yeah. It's just I just figured, you know, it's like I've managed to actually live without them for a long time now because I just buy the case. So I've never really missed them. So didn't know if they're still making those or not. Nice. Right. So then if you take out, so this is your muscle fiber, right? So you can see how that T tubule system, and I love this image for that. It shows you how it just basically surrounds it in all three dimensions. So the muscle fiber itself is permeated by this T tubule and by the sarcoplasmic reticulum. So it's completely draped in the system. And then if you pull out a myofibril, right, which is this cylinder of actin and myosin, you can see the striations now. And the striations are actually caused by the sarcomeres. And we'll take a look at how that is. And of course, they go one step more. From your myofibril, you can pull out your actin thin filament, and you can pull out your myosin myofilament. The one thing I really like about this image is because they are accurate here. Take a close look here. Notice how the myosins are surrounded on all sides, all three dimensions, by an actin. And an actin is surrounded on all three sides by myosin for the most part, right? So you can see that when you're talking about the overlap, we're going to see it in two dimensions. But remember that the way that myosin and actin are arranged is in all three dimensions. It's a three-dimensional cylinder that you actually see. So you can actually see a lot of how it's attached. And you're pulling in all three dimensions, basically. So this is kind of like a nice sort of top to bottom. If you're like studying muscle structure, endomysium, paramysium, epimysium, this is a really, really good image to study from top to bottom because it takes you through all the mesial liners, and then it also kind of takes you down beyond the muscle fiber level down to the myofibril level and the basic construction of the T tubule system and the sarcoplasmic reticulum system within the muscle fiber, as well as the arrangement of the actin and the myosin myofilaments within the myofibril bundle. So this is a really, really good image to sort of go down top to bottom. By the way, this is a really good image to actually take all that information that we talked about in terms of structure. Notice how big and blank it is. It's a really good image to basically write all that detailed notes on as you walk your way from one image to the next. So that's this image, this particular slide is screaming at you for that. Right on me, it's saying. Does it make sense? Okay, so what we'll do is, this is a perfect breaking point, is on Thursday, we will start off with sarcomeres, which should be a lot of fun. No sarcasm intended.